Hello all, and welcome in this new session of this course on pre-MBA statistics or pre-business school statistics. Okay. Now we'll sort of delve deeper into a slightly entirely different angle called as probability. So again, I'm very sure that many of you might have heard about this term, but there might be some issues, there might be some problems understanding probability. So all the things will be clear once we'll sort of have this session and the subsequent sessions. Okay. So in today's session, we'll focus more on some basics, some terminologies, some definitions, some basic ideas, okay? And the entire thing would be in a sequential sort of a manner. So we'll start with very elementary definitions, and then ultimately our goal is to find probability of basic problems and then sort of tell more about, let's say, permutations, combinations. So we'll talk about different notations and slightly different idea from what we've been covering so far, okay? So again, the whole idea, just before we start with the slides, is just to mention quickly is that once you sort of analyze the data set descriptively, we've been doing it so far, creating plots, charts, right, finding some descriptive measures, mean, median, mode, variance, etc. And then in the last session, we sort of analyzed a case study also towards the end, okay. But now we are sort of putting some model to the data set, okay. And then again, probability is not a model, but probability might be a starting point to create a slightly hi-fi model. Okay. So, we will see that what exactly you mean by probability and then some again further notations as we discussed. Okay. By the way, so probability means what? So, probability is chance of anything happening. So, you might have heard about this definition quite often, that chance of an event happening or chance of something happening, etc. Okay. But then we will delve slightly deeper into a bit of notations, and then we will discuss that how do you tie all the things down to find out, let's say, probability of certain event or probability of something happening. Okay. Okay. So now the first thing, and rather the first very important thing to understand, again, like I said, couple of definitions about sample space and events. So you have two different things, sample space and events. Okay. Now before you understand any of these things, sample space, events, probability, etc., things always start with some experiment, isn't it? So experiment could be as simple as tossing of a coin, rolling of a die, or it could be slightly advanced also, let's say performing a clinical trial or doing something in the lab. Okay. So don't be confused when you say experiment, don't try to link it directly to some lab setting. Okay. Experiment is some experiment you can perform which sort of generates some data. Okay. So experiment, like I said, could be as simple as going in a field and collecting data on how many insects you see in the field. This would be a valid experiment. Okay. So let's say once you fixate on some experiment, so I'll take an example, let's say tossing of a coin, okay. And by the way, this slide will discuss number of examples, but let's say tossing of a coin. So tossing of a coin is a very simple experiment, okay. So then the set of all the possible outcomes of an experiment is called as a sample space, alright. So again, just to repeat, so set of all possible outcomes of the particular experiment that you are sort of carrying out is called as sample space, denoted by capital S usually. So again, let's say the experiment is as simple as tossing of a coin. So if you think that you're tossing a coin, what are the possible outcomes here? So the possible outcomes are only two, right? Heads and tails. Okay. So this set, heads and tails, would be nothing but the sample space for that experiment. Make sense so far? So now, as discussed a short while back, we'll cover a few examples and then things will be even clearer. Now let's say the first one. So if the experiment consists of identifying the gender of a newborn kid or a newborn child, then what might be the outcome? So girl or boy. Okay. So in this case, my sample space could be either girl or either a boy. Okay. And usually we denote sample space and write the sample space in curly brackets. So for example, this is the coin example, or this one is the gender example. So all possible outcomes you write down within curly brackets with commas in between. Now the second example, so suppose we are interested in identifying the amount of dosage to be given to a patient until he reacts positively. So this is a slightly advanced example as compared to, let's say, tossing of a coin or identifying the gender of a newborn. But what exactly is the example? Suppose you are interested in identifying the amount of dosage to be given to a patient until he reacts positively. Now again, remember a couple of important points here. So the focus is to find out the amount of dosage. And then second important point is until the patient reacts positively. Okay. So, can you imagine this example in your head and then think that dosage, the amount of dosage can be any number, isn't it? I mean, let's say if you try to quantify the amount of dosage by 1, 2, 3, 4, 5, 6 and so on. So, I can actually give one dosage and the patient reacts positively. If not, you might have to increase, let's say 2, 3, 4, 5, 6. Okay. So, would there be any endpoint to this, or rather would there be any upper bound to this? The answer is no, right? I mean, since you don't have any upper bound, so one can actually give a very large amount of dosage also, right? 10,000, 1 lakh, whatever. I mean, these values are possible, isn't it? So, if any value is possible of the experiment, you have to include in the sample space. Okay. So, now I will tell you the sample space. So, sample space here looks like any real number between 0 to infinity. So, again you may pause the video, try to think about this statement. Is it correct? Is it not correct? So, what do you think? So, amount of dosage, like I said, can be any number, any positive number. So, now of course, amount of dosage cannot be negative. Okay. So, amount of dosage can be any positive number, and hence sample space has to be any real number between 0 to infinity. Okay. So, again hence like I said, sample space could be as simple as only 2 values, for example, GB here or HT there, or slightly more advanced where you have any real number in an interval, etc. Okay. Now, the third experiment is if the experiment is as simple as rolling a die. Okay. And then what would be the sample space? Sample space is nothing but 1, 2, 3, 4, 5, 6. So, the top face, the number in the top face which you see. So, it could be either 1, 2, 3, 4, 5 or 6. Okay. So, hopefully once you get the idea of sample space, then identifying events, then probability would be simple. Okay. So, in this slide we have done with the first entity, which is sample space, and now the second important guy in the room is what do you mean by an event. Okay. Now, any event is nothing but collection of a few outcomes of an experiment. Okay. So, collection of a few outcomes of an experiment. So, again the coin toss example, if you remember, what was the sample space? My sample space was heads and tails for the coin toss example. Okay. So, one of the events could be simply head, or another event could be simply tails. Make sense? So, hence an event is nothing but a collection of a few outcomes of whichever experiment you are performing, and they are usually denoted by capital letters, say E, F, G, etc. Okay. Now, again we will talk about the 3 examples we saw in the first slide, and then we will talk about what might be an event. So, again in the gender example, an event could be that the girl is, or rather the child is a girl. Okay. So, again we saw that the sample space contained 2 options. So, either a girl or a boy, gender of a newborn child, and one of the events could be that the newborn child is in fact a girl. Now, pause the video and then tell me any other event possible. So, the other event which is possible is child is a boy. Okay. Very good. Okay. Now, how about the second example? Second example was slightly advanced rather. So, where you had to find out the amount of dosage until the patient recovers or rather treats positively. Okay. So, in the dosage example, an example of an event could be the amount of required dosage is less than 2. This is one event, isn't it? Because amount of dosage, if you put a restriction on the amount of dosage which has to be less than 2, you are kind of truncating the sample space. And again you go back to the definition of an event. So, definition of event is what? Event is nothing but a collection of a few outcomes. So, whenever the amount of dosage is less than 2, that is an event. Otherwise, if the amount of dosage exceeds 2, that is not an event. Make sense? And the third example, in the dice example, an event could be rolling of an even number. So, again remember what the sample space was. So, sample space was all the numbers between 1 to 6, and the event could be once you roll a die, you get an even number. So, even number corresponds to 2, 4 or 6. Now, why is it necessary to understand events? Because when we talk about probability, we often talk about probability of these events. We will see very soon, but the idea is we want to find out the probability of a certain event happening. For example, what is the probability that the newborn child is a girl? Or what is the probability that the amount of dosage required until the patient treats positively has to be less than 2? Or in the third example, what is the probability that if you roll a single dice, the top face shows an even number? So, hence when you want to understand probability, defining events is at the more important, because ultimately the probability revolves around probability of a certain event essentially. Okay. Okay, so now the next important thing is understanding Venn diagram. So again, I am very sure you must have studied this rather in somewhere in school or maybe early days of college. So any probability course sort of exposes you to Venn diagrams, but what exactly are Venn diagrams? Okay. So again, if you see 3 different graphs here, and all the 3 graphs are called as Venn diagrams individually, of course. So we'll try to explain, let's say 1 or 2, not all of them. So in the very left graph, you see 2 events, E and F. Okay, so these circles denote 2 events, E and F, and then these 2 events are such that there is something in common also. So this shaded area in between is common between E and F. Okay, and on the outside, the rectangular box, by the way, in all the 3 examples denotes the sample space. So you have the overall sample space, and within the sample space you have these 2 events, E and F individually, but these 2 events have a few things in common also, or a few observations in common also. Okay. Now, if you shade this entire region, okay, so just focus on the shaded region in each of the 3 examples. So in the left example, if you focus on the shaded region, so which part have we shaded? We've shaded the entire thing, E and F. So this shaded region is called as union between E and F. So this notation that you see here corresponds to union between E and F, and then notation is E, and you write down something like U and then F. So E union F. So union means what in English? Union means rather E or F. Okay, so maybe you should remember this from now on, that union between any 2 events means E or F. Now again, why E or F? I will give you an example. So again, consider 2 events E and F, and then each event has a number of observations. Okay, so there might be a few observations here within E, there might be a few observations within F, and there might be a few observations which are common between E and F. Okay. So I will give you an example. Let us say you pick an observation, that observation falls here. So which event the observation falls into? E, isn't it? Now a second example, let us say you take an observation, the observation falls here. Okay. So which event the observation is fallen into? F. Okay. Now let us say the third example, again the observation falls here. So now which event it falls into? Again F. Now in the fourth instance, let us say the observation falls here in between, and this is the common area between E and F, isn't it? So hence overall, if you have any observation and that observation is sort of free to fall either in E or in F or both. So the middle region corresponds to both, by the way, both E and F, isn't it? And hence we say that union corresponds to nothing but E or F. So either here, either in E or in F or both. Okay. Okay, so now shifting the attention to the middle graph. So middle graph is what? So again on the, like I said, the rectangular box corresponds to sample space. You have 2 events E and F, and then E and F are such that there is something common also, and the only shaded region here is this guy, the part which is common, and this guy is called as E intersection F. So again, an alternative notation to denote intersection is inverted U. Okay, and then this guy is called as intersection. So intersection simply means the entire part which is in common to E and F. So you take one event, you take another event, and you simply see that what observations fall in both E and F. Okay, so in English again this corresponds to E and F rather than E or F. So union corresponds to E or F, intersection corresponds to E and F, because again like I said, if you have an observation falling here, it corresponds to both E and F. And now the third one is, so again the rectangular box is X, you have one single event in between, let us say E, I will write down E here, and then by the way the shaded region is not E, but then shaded region is everything but E. Can you see that? So everything but E, so everything outside of E, and then this guy denoted by E and then superscript C is called as complement. So complement of what? So complement of the event E. Okay. So complement of the event E means if you have any observation which does not fall in E, so that area is called as complement of E. So everything without E. Okay. So essentially why are we understanding these 3? Because these 3 are standard and slightly more well known than a few other expressions. So union, intersection and complements. Okay. And by the way, all these 3 are called as Venn diagrams. So Venn diagram is slightly easier to understand both pictorially, visually and theoretically as well. Okay, so there is one more Venn diagram by the way. So let us say you have this rectangular box called as a sample space here, and then you have 2 events E and F, but then those 2 events are such that you have, if you see this blue circle, it corresponds to F, and within F you have another black circle corresponds to event E. So, here can you see that the event E is entirely inside event F. So, this notation that you see here is called a subset. Okay, and why subset? Because event E lies entirely inside or rather entirely within another event which is F. So, we will say that event E is a subset of event F. Make sense? So, you have kind of focused on 4 things, right? Union, intersection, complements and subsets. Okay, so the moment we talk about events, we have a lot of different definitions, different ideas about events. So, the very first thing is called as mutually exclusive events. So, what do you mean by mutually exclusive? So, any 2 events E and F are called as mutually exclusive or disjoint if they have nothing in common between them. Okay. So, notation wise, if you take the intersection between E and F. So, again remember, what does intersection stand for? Intersection means everything which is common between E and F. Okay. So, if you take the region which is common between E and F, that should be empty, isn't it? Because you do not have anything which is common between E and F, because E and F are disjoint or they are called as mutually exclusive. So, how would the Venn diagram look like here? So, if you draw the Venn diagram would look something like this. So, you have 2 circles denoted by E and F, but they do not intersect. Okay. So, the intersection is an empty set, and by the way, this is a special notation to denote empty set which is called as phi, Greek letter phi. So, small example, in the dosage example for a particular patient, amount of dosage less than 2 and amount of dosage more than 2. So, should they be mutually exclusive? Answer is yes, because amount of dosage less than 2 and amount of dosage more than 2, there is no such thing which is common between these 2 events there. Okay. So, again, idea of disjoint events and mutually exclusive events is kind of very important and sort of build up to a couple of other ideas and eventually probability. Okay, so now we have discussed Venn diagrams, a few ideas of probability. Now we are in a position to sort of define probability of any event. Okay. Now the first thing is notation. So once we denote an event, we can talk about its probability, denoted as probability of any event E. Now again, like I said, what do you mean by probability? Probability means nothing but the chance of happening of any event E, as you can see here. So probability of an event E is nothing but the chance of happening of that event which is E here. Couple of examples. So let us say, what is the probability that in a single dice throw an even number will appear at the top? So here, what is the event? So event here is nothing but getting an even number, isn't it? So this is the event here in the example here, and once you define an event, I can talk about probability of that event. So let us say this event is denoted by E. So the question is asking that what is the probability that in a single dice throw an even number will appear at the top. So we are essentially trying to find out probability of the event E here. Okay, so couple of very important properties or other axioms of probability. So again, notation wise, we've talked about that it's sort of denoted by P of E, right? But we'll talk very briefly about 3 important axioms. So any probability value has to lie between 0 and 1 strictly. So of course, probability can be 0 or 1, but it can't be negative and it can't exceed 1 also. And you'll soon see that why this should hold true, okay? Because again, remember that probability is what? Probability is chance of an event happening. Alright. So chance of an event happening has to lie between, as a measure, has to lie between 0 and 1. So this is the first axiom. Second very important axiom is if you take probability of the entire sample space, what should that be? So probability of the entire sample space has to be 1 always, isn't it? Because if you take the entire sample space, one of the events should automatically happen at any given time point. So probability of the entire sample space occurring has to be 1. And the third important axiom has to revolve around the idea of mutually exclusive, unions and so on and so forth. So now imagine that you have number of mutually exclusive events. So this is important, mutually exclusive or disjoint events, and then how are you denoting them? So E1, E2, E3, E4, etc. Okay, and let's say that you have some n of those, so up to En. Okay, and then again all these are mutually exclusive. So again, what do you mean by mutually exclusive? So if you take any pair or rather any triplet or any bunch of these events, all these events are sort of mutually exclusive, or there is nothing there in common between any 2 or any 3, etc. So probability of union of all these events. So what do you mean by this? So this is denoted by E1 union, E2 union, E3 etc., all the way up to let us say En. So, this is what it means, the LHS. So, probability of and then you have to put a probability of course. So, probability of union of all these events is nothing but summation of individual probabilities. And by the way, we will not prove it here, but again intuitively it should make sense, because let us say, so how would the Venn diagram look like? So, let us say you have this bigger S or bigger sample space, inside which you have number of all these events, and all these are mutually exclusive. So, this is E1, this is my E2 etc. Okay. And probability of union of all these disjoint events is nothing but summation of individual probability. So, probability of E1 plus probability of E2 plus probability of E3 etc. So, these three axioms sort of happen to be the bone or rather the base of all the slightly more advanced proofs, properties about the probability measure P. Okay, so now the next thing is, you must have studied this again in college or somewhere earlier, permutations and combinations. So, what do you mean by that? So, permutations and combinations, you have two different angles. So, firstly we will talk about permutations. So, permutations means in how many ways can you arrange a few n items in a sequence or in a line. So, how many items are there? You have n items, and you want to simply arrange those n items in a straight line or in a sequence. So, imagine that you go to a library and then you have all these library shelves, and if somebody tells you that can you arrange let us say 10 books in a sequence on a library shelf. Okay. So, arranging 10 books in a sequence would be permutation. So, permutation means what? So, let us say I will give you a simple example. Let us say you have 3 books. Okay. So, B1, B2, B3. So, you have 3 such books. Now, can you tell me that how many ways can you arrange them in a line? So, I can actually have this sequence, or I can actually have B1, B3, B2 also, isn't it? So, the first book is B1, second is B3, third is B2, or I can start with B2, then I can have B1, B3 and so on, alright. So, to find out in how many ways can you do such a thing is called as nothing but the permutation. So, in how many ways? So, again definition says in how many ways can you arrange, isn't it? So, B1, B2, B3 is just one way, B1, B3, B2 is another way, B2, B1, B3 is yet another way. So, in how many ways can you arrange 3 such books? And the answer is n factorial. So, here the answer would be 3 factorial, which is 6. Now, again what is factorial? Factorial is nothing but, if you have n factorial, is nothing but n into n minus 1 into n minus 2 into n minus 3 all the way up to 1. So, 3 factorial would be 3 into 2 into 1, which is 6. Okay. Make sense now? And then this is basically the technical definition. So, it means that in how many ways can you arrange r items out of n items in a sequence. So, by the way, this was a special case. So, keeping a few books on a library shelf, let us say you have 3 books, and in how many ways can you arrange all the 3 books in a shelf? Answer is n factorial. But now a slightly advanced thing is, let us say if you have 3 books, but I need not arrange all the 3 books, I want to only arrange 2 books in a sequence. So, in how many ways can you do it? So, 2 books means what? So, B1, B2, B1, B3, B2, B1 etc., etc., isn't it? So, you have 3 books by the way, but I am not focusing on arranging all the 3 books on the shelf, I want to only arrange 2 books out of 3. So, then how would things change? So, this is the formula that you have. So, in how many ways can you arrange r items out of n items in a sequence, and this is exactly a standard notation of permutation. So, it is denoted by permutation P n comma r. By the way, this P is not the same P we have seen earlier in probability. So, do not mix it up. So, this is a permutation notation P n comma r, and the answer to this question is n factorial by n minus r factorial. So, in the books example, how many books you have? So, you have 3 books. So, numerator is 3 factorial. And how many books you want to arrange? I want to only arrange 2 books out of 3 books. So, it would be 3 minus 2 factorial, which is 1 factorial by the way. So, the answer is 3 factorial, which is 6. Make sense? So, first idea is permutation. Permutation means arranging a few items out of n items in a sequence. Now, the second idea is combination. So, what is combination? So, combination is slightly different. Combination means in how many ways can you choose r items out of n items. So, here the focus is more on let us say picking or choosing how many items, again r items out of how many items, n items. Now, again the key difference between combination and permutation is in combinations you need not arrange them in a sequence, you are simply choosing them, okay, and hence the formula reduces to n factorial by n minus r factorial into r factorial. So, by the way, since you are not arranging them in a sequence, you are simply choosing r items out of 2 n items. Again, going to the library example, let us say if you have 3 books, in how many ways can you pick 2 books? Okay. So, I can actually pick book 1, book 2, I can pick book 1, book 3, or I can pick book 2 and book 3. So, I only have 3 choices. So, can you see that the combination value is always smaller than the permutation value, because there is no requirement of arranging the 2 books in a sequence there. Okay. So, hence note that in permutations order matters, whereas in combinations it does not. So, hence combination is always smaller than permutations. Okay. So, understanding permutations, combinations, a few problems is sort of important to understand the idea of probability or other idea of counting techniques. Okay. So, we will end this session by sort of describing conditional probability very briefly. So, we studied probability, events, etc. Now, what do you mean by conditional probability? So, conditional probability of let us say 2 events E given F, and we will say that let us say you have 2 events out of which F has occurred, or you are kind of assuming that you know something about F. Okay. Now, notation to denote conditional probability is PE, probability of E given F. So, given is denoted by a vertical line like this, and how do you denote it? So, the conditional probability is nothing but intersection in the numerator divided by probability of whichever event which you assume to be have occurred, which is F in this case. Alright. So, the conditional probability on the left hand side is nothing but intersection between 2 events divided by probability of F. So, just to give you a simple example, how do you quantify conditional probability? So, simple example, let us say what is the probability that it will rain today given that it is cloudy? So, can you spot the 2 events? So, event E in this case would be it will rain today, and event F in this case would be it is cloudy today, and ultimately you want to find out probability of E given F. So, given that it is cloudy, what is the probability that it will rain today? So, of course, this probability will not be exactly same as simply saying probability of E, is not it? So, probability that it will rain today would be different, and then probability that it will rain today given that it is cloudy would be different. Okay. So, imagine that this structure is called as conditional probability, and then very last thing is what do you mean by independent events? Okay. So, independent event means that if you take the intersection of 2 events, then probability of intersection should be product of individual probability. So, independent events means one of the event has nothing to do with the other, just to summarize. So, to give you a simple example, tossing a fair coin 2 times, event E denotes getting ahead on the first toss, event F denotes getting ahead on the second toss. So, can you imagine this in your head that if you have two coins, you are tossing the 2 coins, and event E denotes getting ahead on the first toss, that has nothing to do with what the outcome would be on the second toss, isn't it? So, in this case clearly getting ahead on the second toss is not affected by getting ahead or tail on the first toss. So, these 2 events E and F are entirely independent. Okay. So, in the next session we will see that how to build upon let us say a few other ideas of probability and couple of other definitions, and eventually we will focus more on what you call to be as random variables, distributions, etc. Okay. Thank you.